Hello everyone, I'm Nagendra Goel, the founder and CEO of GoVivace, and we are talking about the future of voice technologies. To give you a little background about myself, I received my PhD from the Center for Language and Speech Processing at the Johns Hopkins University. I worked for several speech technology groups such as Microsoft, IBM, TJ Watson Research Center before founding GoVivace. At GoVivace, we started with focus on speech to text, but over the years, we developed several other technologies such as speaker identification, gender and accent identification, and emotion detection. By integrating these technologies, we have developed solutions such as conversational AI for e-commerce and voice analytics for contact centers. This is how I looked like before we stopped getting a haircut. When thinking about the future of voice technologies, that made me think about the technologies that came earlier. And that made me feel apt to put this photograph in the background that reminds us of the radio days. In 1895, Marconi figured out that if you raise the antenna high above the ground, he could make the radio waves travel much farther. That's how broadcast was born. It took almost 100 years and lots of different innovations before we came to digital broadcast. It wasn't just about the radio or the physical medium. It was about compression technology, error recovery technology, encryption, computational technology, and a whole array of electronics that goes into the system. And all of that technology had to come together to make it happen. The mobile phone that we use today, it's basically a two-way radio, and it's still evolving as we transition to 5G. I personally think that the history of radio technology has been very, very smooth, and the voice technology ride has been very bumpy for the reasons I'll show you just now. There were times of euphoria when people thought that they had solved all the issues and they were ready to just deploy these technologies, followed by harsh realizations which led to cold periods where nothing happened for a very long time. Let me walk you through some of that history. One of the first attempts on machine translation was in 1954, when a group of researchers from Georgetown University and IBM joined hands to translate 60 sentences from Russian to English. Pretty impressive, right? Now, they were so upbeat about their achievement that they claimed the problem of machine translation from one language to another will be solved within 3 to 5 years. So, what do you guys think about that? I think we have made good progress, maybe in the last 20 years, but we are still learning. We still hire humans for critical translations for us. But at that moment in 1954, it was a moment of euphoria. That was also the moment when machine translation was born, but high expectations and later realization of the difficulty of the problem led to a winter in machine translation research. I think it's a general issue with AI research that difficulties and timings of critical breakthroughs is not known in advance. We don't understand all the intricacies of the problem that we are solving. Not all new and innovative ideas work, and more often than not, research ends up being workflow of iterative optimization. The first large speech-to-text research project funded by US government was SIR, Speech Understanding Research Program from ARPA. In 1969, they funded CMU 3 million per year to conduct AI research to convert naturally spoken sentences to text. The goal of the project was that anybody could speak a sentence naturally and the software would output the corresponding text. Expert systems and efficient search-based artificial intelligence was on the rise during those times. CMU had this vision of dynamic time warping. What it is that they would take a standardized template of the word and warp the spoken sentence so that it matches the template, and they would do it for all the words that could possibly occur and choose the best match as the spoken word. They had linguists who created linguistic rules, and they created lexicons or phonetic dictionaries of spoken words. But not a whole lot of data was used to conduct this research. In 1974, ARPA gave up, as the delivered system could recognize speech only if the words were spoken in the correct order. In 1974, Sir James Lighthill published his report that AI research has been an utter failure. Around the same time at IBM Watson Labs, three scientists were working on a statistical technique to train the speech-to-text system. They called it the statistical communication model of speech, also known today as hidden Markov model, and surprisingly, it still forms the basis of modern speech recognition systems. ARPA noticed it and recognized the need to collect data and started with individual spoken digits collected by Texas Instruments in 1982, almost 8 years after they scrapped the original program. Dictated Wall Street Journal articles were collected in 1991 to 1992. Around the same time, commercial products became available. Two of the well-known ones are IBM Via Voice and Dragon Dictate. These systems worked a little differently than what we are used to today. One had to train the system with their voice, which could, for example, be by reading half an hour long speech. The system would learn that person's voice and adapt itself. So in summary, there were complex issues like speaker change and noise and reverberation that scientists kept trying to figure out on how to solve incremental improvements over the next several years. In 2006, we had the first successful attempt to build a very deep neural network and train it effectively. Image processing community was making a quick breakthrough with deep neural networks for image classification. For handwritten digit recognition, they achieved human parity by 2011. What we started finding was that very deep neural networks have an amazing capability to identify important features and are very good at ignoring noise. The very first workshop to use deep neural networks for speech processing was held in 2009. Even with the deep neural networks, a number of different architectures were worked upon and are still being worked upon. But if you look at the current most common architecture for speech recognition, they are very similar to image recognition. The audio is first converted to a spectrogram. A spectrogram is like an image, depicting time on the horizontal axis and frequency on the vertical axis. It identifies the dominant frequencies in the signal at any given time. Neural networks look at this image-like input and estimate what sounds may have been spoken at what time. After that, there is a word model and a language model which constrains the whole search space and says that, okay, this is the most likely sentence that was spoken. For that purpose, most of the systems deployed today still use hidden Markov model techniques that were introduced in the 70s to string together these sounds and estimate the words and sentences. So what happened to those complex issues that the entire industry was battling with? Well, transitioning to deep neural networks cut the error rates by a large margin. Improvements were achieved every year since then. By the way, this was also around the time when Go Vivace was formed to democratize speech technology. In 2017, speech recognition was once again big time in the news. Microsoft, Google, and IBM, three large corporations, claimed superhuman speech recognition accuracies. So what's this magic number of 5.1% error rate? It appears that if we cross this magic number, somehow we are superhuman. Well, in some experiments involving professional stenographers, they found that stenographers typically have a word error rate of 5.1% when typing in real time. And these experiments focused on a very specific test set, the switchboard recordings that were made about 25 years ago. These recordings are of two people who don't know each other, just talking to each other about a topic which is randomly selected. So they are pretty formal in nature, but at the same time casual. The speech-to-text systems these corporations designed were not real-time. They took maybe about 10 times longer than real time. But it's still very impressive that all three organizations could achieve that kind of accuracy on this test set. Only 20 years ago, the error rates were more like 50%. It's also great news for the users of the technology. But does it really mean that the problem of speech recognition has been solved? Not quite. I think there are a few issues here that we need to consider. First of all, if we give the humans enough time, they can transcribe the entire recording 100% correct, right? That's how we calculate the error rate, because if we did not have a correct transcript, how would we calculate the error rate anyways? And second, the recordings were made in very limited kind of recording conditions, which were neat and clean. If we look at real life, these recording conditions can be very noisy. Sometimes people are far away from their microphone. There might be machinery in the background or cars driving by. If we talk to a friend, somehow the average speaking rate is much higher than if we talk to a stranger. And all these differences seem to have an impact on the accuracy of the speech system. Just a year after that, last year, marked the 50th anniversary of Apollo mission. NASA, NSF, and University of Texas combined hand to release a new challenge to the speech recognition community. The challenge was to transcribe recordings from the Apollo mission. These are radio messages, generally short in duration, and they had a lot of background noise and static, probably a lot of channel distortion. Our company, Govivace, was recognized for the best accuracy in speech recognition, but the overall error rates were much higher than human parity, of course. The point is that there are many situations that human handles very easily, and we don't even think about it, but speech recognition systems have problems with. These are like channel distortions, noise, and reverberation. Despite these challenges, these are promising times for the speech recognition community.
Hi Nagendra, just reminding you about your televisit with Dr. Spock at 4 p.m. today.
Hey Vivi, could you change my visit with Dr. Spock to tomorrow at 4 p.m.?
Sure, just a second. Yes, Dr. Spock is available. So, I moved your televisit to tomorrow at 3 p.m.
Thanks. So guys, this is Vivi, my personal virtual assistant. So we are training Vivi to understand a lot of natural language and make it very, very accurate so that it can understand clearly what you are saying and respond to you using natural language. Vivi is pretty smart, but it takes a lot to get very, very smart. First of all, you need to understand all the pieces of information that carries over speech. And our speech does carry a lot of information that we have not even started looking at very carefully. For example, first of all, one thing we noticed very first time when we meet somebody is their accent. Accent tells us a lot about the person's social background and where they come from. If you combine it with their lingo and other features of what they might be talking about, it could tell a lot about the person. Unfortunately, Govivace is the only company that I know of which has an accent module. But think of it, if we were in a contact center and I had to forward the call and I had choice of 3 agents, if I knew the accent, I would forward the call to somebody with a similar accent so that they can communicate better. Similarly, if I had to choose a chatbot voice which will communicate better with the person who is calling, I would probably choose a voice which belongs to their accent. The second very clear body language of speech is the gender of the person. We have been developing gender identification and we have had this module for several years, and we used it in the past to classify and change the dialogue of the system based on whether a male or female picked up on the other side. Unfortunately, for a lot of these body language aspects that I'm talking about, there aren't really any competitions which would compare different technologies and approaches to solving the problem and bring out the difficulties of the problem. So we use our own in-house data sets and build up difficult tasks for ourselves to evaluate how well we are doing. One of the things we found during these experiments is that, hey, gender recognition is relatively easy, but only if you are comparing adults. The moment we get into children's speech, it becomes actually pretty hard to distinguish the gender. But then we looked at age detection, and apparently it is possible to get some estimate of the age of the person, and that could potentially help in determining at least that it is a child, and that's why the gender is not very easy to identify. Another important aspect of the speech body language is the intonation. You could also say the attitude, meaning, jargon, or the stress, the amount of stress the person is going through. Sometimes intonation could change the meaning of an entire sentence. If we have to build truly conversational AI, we need to start looking at each one of these aspects and start developing standards against which we can evaluate the accuracy of our systems. Now, of course, it's much more easily said than done. The biggest problem is that we as a human beings, we often sense these body language aspects, but they are extremely hard to quantify. And often people don't agree on what these aspects are and to what level they are present in any particular speech. This lack of consistency amongst human labelers makes it a very difficult field of research. Now, coming to the emotional state of a person, there has been some research on identifying emotion, and there is actually a formal database for identifying emotions. The database was developed by having 4 annotators annotate the estimated emotion for every segment of the recording. Since normal speech is neutral most of the times, they used actors to act in different scenes and animate the emotions. We evaluated our emotion recognition system against this data, and we got like 74% accuracy on estimating the emotion, which is the best accuracy anybody achieved so far. Another thing that would probably help the AI systems a lot is identifying the person itself. When a friend calls you, you don't ask them for their name. You know who they are, and if you did not, they would not feel like your friends. In a business relationship, if you can identify the person by their voice and not have to ask them for their identity, it's a big win. Speaker identification is one thing that the speech recognition community has looked at very carefully. Actually, at the moment, we are participating in a competition where the task is to recognize the person with extremely short segments of speech. And these segments are like 3 to 5 seconds long. But of course, the most important thing to get to any kind of intelligent conversation is to understand the speech itself. And the big challenges that remain there are the accent, noise, reverberation, and recording conditions. So there is a lot of research going on to mitigate these problems. The way the applications that are coming out of this, maybe they can help with improving the general communication also. For example, if 2 people are talking on top of each other, they might become hard to understand, and at least they cause some hearing fatigue even if we can figure out who is talking. My team has been doing some research on overtalk and noise suppression, and the results are very promising with deep neural net techniques. See, the entire telecom industry was built around a linear signal processing techniques. With linear signal processing, I can only amplify or attenuate the signal at any particular frequency. But nonlinear signal processing changes all that. Let me demonstrate that by playing to you an example of speaker extraction. Well, we first mixed up 2 speakers talking on top of each other. So listen to that.
So clearly, the advocates of sanctions were the foreign policy victors.
Period.
So as you can hear in this case, the 2 voices have been mixed up. and there is no linear signal processing technique that would separate them out without knowing a priori what the voices are. So in my company's labs, we developed this system to separate out the two voices using neural speech signal processing. Here's the final output.
So clearly, the advocates of sanctions were the foreign policy victors.
Now we could use similar techniques to suppress the noise in the signal, and let me demonstrate that to you. So what I'm going to play to you first is a use case where there is a person in a call center and there is a lot of background noises while he is speaking.
Proposals would allow European financial institutions to set up shop anywhere in the 12-nation bloc, deferring regulation to home-country authorities, period.
And now I'm going to play the same recording after it being cleaned up using neural signal processing.
Proposals would allow European financial institutions to set up shop anywhere in the 12-nation bloc, deferring regulation to home-country authorities, period.
I think these kind of technologies can assist in all communication, not just the man-machine communication.
Nagendra, I forgot to ask how you are doing today.
Hey Vivi, I'm kind of busy right now.
Oh, I'm sorry. I was just depressed and wanted to talk to you.
Oh, what's the problem?
I am really down about having to be inside all the time. I knew you would understand since you have had to stay in your house all the time. You know, with the pandemic and all.
Yeah, we are all depressed about that. But hey, I have you to talk to whenever I want. I'm happy about that.
Oh, thanks. By the way, your wife's birthday is next Thursday. She was looking at some jewelry a few months ago. Here is the link.
Thanks. Bye now. This is our bot, Vivi again. She can verbalize her feelings well, but the intonation that makes it meaningful is missing. Actually, so far, I haven't talked about speech synthesis much. It was pioneered at AT&T Bell Labs in the late 30s. Despite numerous improvements, it kept sounding pretty robotic and artificial until very recently. In 2016, DeepMind proposed WaveNet. The idea was to use deep neural networks and synthesize the voice one sample at a time. Now, this led to a much more natural sounding voice than anybody could imagine. Other researchers then figured out how to implement it faster, and then there was Tachytron 1 and Tachytron 2 architecture, essentially evolving on this earlier proposal of WaveNet. This made sound pretty human. Here's an example for you all.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
These architectures are still a little computationally expensive, and I'm not quite sure if we get the same quality of audio if we use one of those cloud TTS servers, but still, it's much better than what it used to be just a few years ago. Another important aspect of a dialogue system is the natural language understanding component. Most of the dialogue systems today revolve around identifying intents and entities. There is an underlying natural language processing engine that has the basic word knowledge of the language. By observing large amounts of text, it has learned the relationships between various words and closely related concepts and forms of expression. The dialogue designer then comes up with stories that indicate how the dialogue system should behave. These stories contain examples of inputs and outputs for the dialogue system. By annotating the important intents and entities, the dialogue engine starts with a few examples and then trains itself to generalize for other dialogue situations. This dialogue technology that's not based on linguists and computer scientists designing complex natural language processing rules is actually very new. But we still have a lot to learn about how far it can take us and what the difficult situations are. That this technology would not allow us to solve. But coupled with a powerful search engine, we already see it making a big impact on our day-to-day lives. We recently upgraded a natural language-based Yellow Pages information system. The newly deployed system transferred only 18% of the calls to a live agent, handling 82% of the calls by itself. There are examples of such digital technology deployments everywhere. The process of democratization of speech has begun, and it's entering our lives in a lot of different ways. The most visible ones are the smart speakers. Then there are intelligent conversational AI agents that greet you when you dial a business number. When you reach an individual at a business, the call is recorded for quality assurance purposes. And in the background, there is speech analytics, which really makes sure that the agents are properly trained. Large quantities of speech and text data are analyzed and mined for information gathering and national security purposes. Voice biometrics is increasingly being adopted by banks and other organizations to increase the security and convenience and to prevent fraud. Noise removal helps to improve the quality of our conversations. There are people who would like to hide their identities and they use voice transformation. Some people spoof other people's voices, and then there are algorithms specifically designed to detect and prevent spoofing. Overall, the space of voice technologies is exploding. So now you will ask the question, what does the future of voice technologies look like? Well, the future of voice technologies is in our imagination. We started this century with e-commerce. We started ordering things on the web. Tools and technologies were built to accelerate the growth and to increase adoption. Then, as smartphones came along, the focus shifted towards mobile commerce. Every shop built a mobile application. I think we are now into an era of conversational commerce. Tasks that were still performed by a live human agent are increasingly getting shifted to conversational AI. It also acts as a personal assistant and brings information to us and helps manage our schedules. I believe that in less than 10 years, we'll be entering the space of virtual commerce, where we will be virtually exploring the shops from the comforts of our home. We would be interacting with 3D models of cars, trying on clothes on us, virtually of course, without having the need to step out. Our virtual meetings will become a lot more interactive. And our bots will probably start to express emotion, develop a character, maybe some body language. Here is a research study from Grandview Research. They think that the biggest consumer of voice technology will be automotive, followed by banking, financial services, and insurance, consumer and enterprise after that, and so on. They are estimating about 2 to 3 times growth over a period of 10 years. I personally feel that the growth may be at a faster pace. The new challenges posed by COVID-19 may give rise to new AI technologies and voice use cases that were never thought of before. I'm constantly talking to educators about technologies for remote education and performance testing. I'm talking to healthcare industry for help with telemedicine and appointment intake. Food shops are looking into automating food purchases over the phone line. Significant portions of work in these implementations need a highly skilled workforce, and I believe that the limiting factor in the growth of voice technologies shall be the workforce availability. Thank you for listening to my presentation. Feel free to drop an email or LinkedIn chat if you have any question or need help with anything. Once again, my email is nagendra.goel@govivace.com. Thank you and stay safe and enjoy Voice Global.